exactly solvable to the CFTs. Just a small announcement. So this is a set of lectures that is valuable for those of you who need a certificate for the postdoctoral. So if you need a certificate, just put your name here. And if you are from outside CA and want to join us for lunch, stay here. We will give you a card that you can exhibit to the canteen. Okay, so I think it's more or less everything. And I think we get started.
Nobody needs to say. So, once upon a time, in 1997, some people wrote a book called Conformal Field Theory, so the so-called Big Yellow Book. And if you read it, what you find in it is, well, only or almost only two-dimensional conformal field theory. So now, if you wrote a book with this title, nowadays you would expect to have a lot of CFT in higher dimension as well. But if you want to talk about exactly solvable conformal field theories, I think we are essentially back to two dimensions. And so that's the subject of this course. And why is it only in two dimensions? Well, because to exactly solve CFTs with the methods we have, well, we need two essential ingredients. And the first ingredient is algebra of conformal transformation. That is infinite dimensional. And this is the case in two dimensions, as we will soon see, but not in higher dimension. So the other ingredient I will use to solve these CFTs are the existence of degenerate fields. By which I mean fields which, when you take a product with any other field, you find a finite number of terms, modulo conformal symmetry. This can exist actually in higher dimensions as well. So, when we have these ingredients, what can we do? I mean, these ingredients allow us to do conformal bootstrap, numerical or analytic. And if you didn't have that, if you were in higher dimensions, you would need to make extra assumptions, basically, to practically apply this the bootstrap method. In particular, you would often assume unitarity, which restricts the theories you can address. And also, if you want, I mean, unitarity, you can view it as inequalities on some structure constants. But if you want exact results, it's a bit hard to get if you start with just inequality. Okay, so even in two dimensions, actually, the exactly solvable CFTs are not so common. And probably most CFTs are not solvable. I mean, to see that, you can start with some simple solvable CFT, and you can perturb it with a relevant operator, follow the renormalization group flow, and typically you will end up in a rather intractable CFT. So now, which CFTs are we talking about? Yes.
The definition you gave of degenerate fields is not the one I would have in mind. I would have in mind that the correlation function satisfies some linear differential equations. Is it equivalent or is it unrelated?
No, it is the differential equation is a consequence of this finiteness of operator products. Okay, so what are these solvable CFTs? Well, I mean, if you cheat a lot, you can read the outline of the course, and basically here is the list of these solvable CFTs. But well, I would say they fall into two categories. So the Liouville theory and the minimal models, I mean, minimal models plus generalizations, limits, etc. I mean, these are quite well understood, and these are actually solved in the sense that we know the exact formulas for structure constants, and in principle we can compute any correlation function to any desired precision. And then we have loop models. So loop models is a class of models which are believed to be solvable because we have quite a few exact results, but they have not been fully solved. So these loop models are a class of CFTs which emerge as critical limits of various statistical models in various phases. And they have various applications like polymers, percolation, or more recently, Arc-type hydraulics. I found that the other day on the archive. On the other hand, they have, all these exactly solvable CFTs have relatively few applications to gravity. And the reason for that is that if you want, for example, a CFT, which is holographic dual to three-dimensional gravity, then you want, gravity has a weak coupling regime, and that will correspond to the large central charge limit of your CFT. But there are strong technical reasons why these solvable CFTs exist only at small central charge. We will see that. Yeah, so that's a very good question. So indeed, my list of solvable CFTs, you may find it a bit short because we also have exactly solvable CFTs with larger symmetry algebras, what I would call extended chiral algebras, meaning a local algebra which is larger than conformal symmetry itself. And for example, you have theories with W algebras or West-Minowitten models. Okay, so I won't talk about them in order to keep the course reasonably short. And also, the methods I will describe, they generally apply to these cases as well, except that it's more complicated technically. So now, what do we do? When a CFT is solvable, how do we solve it? Well, usually when something is solvable, you can have several possible ways to solve it, giving the same results. And I will focus really only on the conformal bootstrap method, which I think is simpler and more general than the alternatives, such as the Coulomb-Gas method. So the Coulomb-Gas method is based on perturbing free bosonic free field series. And when I mean perturbing, I don't mean that we will get approximate results. In two-dimensional CFT, you can do these perturbative calculations and still get exact results. Another approach is the modular bootstrap, based on exploring the modular invariance of a torus partition function, but I will concentrate on correlation functions on the sphere, and I won't talk about torus partition functions. And in particular, this will allow me to remain rather agnostic about what the spectrum is and whether field belongs or not to the spectrum. And we want to have some flexibility in that respect in order to compute interesting physical observables. So, this approach, this conformal bootstrap is not mathematically rigorous, I would say, or not completely rigorous, although there are attempts to make it rigorous. But my concern will be to derive the results in a rather simple way, without introducing too many constructions which later have to be discarded. Well, still there are some non-trivial calculations as you would expect, and I will sketch some of the calculations in the course. Some of them, in principle, you can do yourself, and actually it's recommended to do them if you want to really learn this material.
So, can you say what your concerns are about the rigor of the bootstrap? Like you had something in mind.
Well, yes. So the bootstrap is an axiomatic approach. So I'm introducing objects and making axioms about what properties these objects obey. But I'm not proving that these objects actually exist. So I can prove to you that the Liouville theory, if it exists, has this or that correlation functions. they won't give a proof that it actually exists. Well, we can test it numerically, for example, but that's not a proof.
Yeah, so I agree it's not constructive, but it is rigorous in its formulation.
Okay, so it is rigorous in the sense that if it exists, then it must have this and that properties. But I mean, in principle, I would want to show that the CFT exists.
Yeah. It seems like different philosophical points of view, but rigor is not the thing in question.
Okay, yeah, if you want.
And so to continue on this, how do we prove that a CFT exists? Is there a case in which you can prove that? Apart from, you know, like, I don't know, perturbation theory, like Wilson-Fisher or something.
Yes, so there are, in the case of Liouville theory, there are, let's say, two approaches to prove that it exists. So one of them is based on vertex operator algebras, and one of them is based on basically probability theory. And in both cases, you want to actually give a construction of the correlation functions, and then you show that these correlation functions obey all the axioms that you have.
Sorry, an aside, separate problem. You said you're going to stick to the sphere. So before we abandon the torus completely for the rest of the course, just a quick question. How much is known about, like, say, minimal model endpoint correlators on the torus? Are those completely solved?
Well, it may depend on which minimal model you're talking about. So I discovered when preparing this course that E-series minimal models may not really have been solved. At least it's hard to find the solution in the literature. A-series and D-series are on the more control. So probably if you want to compute any torus correlation function of an A-series or D-series minimal model, you can do that because you know the structure constants, and in principle you can compute the conformal blocks. So you combine all of them and you get your correlation functions to some accuracy. Okay, so the plan, well, the plan is first to introduce the basic of two-dimensional CFT, which means first the conformal symmetry, which algebraically means the Virasoro algebra and its representations. Then to-be fields and the operator product expansions, and then correlation functions. So this should take us about the first two courses, hopefully a bit less. And then I'll come to sketching the solvable CFTs, in the sense not of solving them yet, but at least of arguing why they should exist, which properties they should have, what are their spectrums in particular. And after that, we come to the analytic bootstrap, which is finding exact relations for the structure constants of these theories. And that's done by studying degenerate 4-point functions, which obey the Belyavin-Polyakov-Zamochnikov differential equations. Then, after that, probably we'll be running behind schedule. So I already anticipate that the part on numerical bootstrap will be will be somehow sacrificed. I mean, that's a technical subject anyway, but I probably want to only to sketch what this consists of. And then I come to correlation functions in loop models, which is a subject where results are a bit more recent, meaning some of them in the last months. So let's start with and with conformal symmetry on the two-dimensional sphere. So that's 1.1, the Virasoro algebra, and its representation.
So, one of the goals of the course, presumably, is to identify principles that allow us to solve the solvable theories, and then look for the theories that we can solve and solve them. Can you give us a suggestion of like what these principles might end up being, or what extent you have such principles?
Yeah, so I would say the principle start with studying the fusion rules of degenerate fields. So we will build some algebra of degenerate fields. And this will already give us strong constraints on what the spectrum is. I mean, I'm not using modular invariance on the torus, so I have to do something else to get the spectrum of a minimal model, for example. And the way we will do it is to generate them by fusing degenerate fields with one another. So this also will constrain, for example, the spectrums of loop models. And so that would be the basic technical ingredient. And then when you want to study correlation functions, you use this technical ingredient to look at these degenerate 4-point functions and derive differential equations. And I mean, these ingredients, I think, would work also in other CFTs, which I'm not mentioning. So either in with higher symmetry algebras, like W algebras, or even non-solvable CFTs, where you wouldn't want to solve them completely, but only to get some constraints and relations on correlation functions. So yeah, that's one of the goals, to introduce these methods. And the other goal probably is to have a kind of panorama of what is known on solvable CFTs with just Virasoro chiral symmetry. Because I think, well, not all these results are very well known, and they are not really gathered in any coherent presentation, I think. So, in particular, the stuff about limits of minimal models, and of course, loop models.
Are you saying that imposing that the theory can be consistently defined on a torus or higher genus, it does not impose any more constraints? All the constraints that would come from that, you can also derive just.
Not quite. I mean, if you impose consistency on the torus, it gives you more restrictions. But I mean, you can have a very plausible argument for minimal models without referring to the torus.
So then some of the models that you can construct on the sphere, if you don't impose any more constraint, they would not be defined. They would not be consistent with it.
Yeah, well, right. But I mean, one of my points would be that the notion of a consistent CFT should be a bit flexible. I mean, for example, if you consider the Ising model, the minimal model, you just have a few fields, but if you want to compute, let's say, cluster connectivities, I mean, that's not done with these fields. You have to introduce extra fields. And you don't really want to worry about whether you're breaking or not modular invariance by doing that. You just have this physical observable you want to compute, so let's compute it on the sphere. And if you start worrying about modular invariance, well, I mean, that's really a formal constraint which does not really help you.
So there are actually two notions. There is the sphere CFT and the general CFT.
Well, it's not only about the sphere, it's about focusing on correlation functions, really. I want to focus on some space of correlation functions instead of on, let's say, partition function or on a fixed spectrum.
Just to close the circle, from that point of view, you know, if you were to find out later that theory so constructed was not modular invariant, would you care?
So if I was to find it was not modular invariant, I would just say, well, please add anything you want in it to make it modular invariant, so long you don't spoil my nice observable which I wanted to compute.
And then suppose I say, okay, and then I go and try, and then it's not possible, and there'd be other contributions or something. How would you feel about that? I mean, does that happen?
I think it would always be possible. You just add a bunch of stuff, and then even if you don't really understand that stuff, well, it makes it modular invariant.
But it might affect your correlator.
Well, not necessarily, because in my correlator, I mean, what appears is fixed not only by the spectrum, but also by the fusion rules. So I can always say that the fields which I need for that correlator, they have this or that fusion rule. So this fixes whatever fields appear in the S channel, for example. So my correlator would not be affected by what I add to the overall spectrum.
But it might not be up to you, right?
Okay, so I think we'll have a more extended discussion of this point at the beginning, actually, of this section too, because then I will discuss what we mean by a CFT, in fact, and its structure. Okay, so the Virasoro algebra. So why the Virasoro algebra? So we want to do CFT on the sphere. I mean, the Riemann sphere, which is C bar, meaning C, the complex number, plus some point at infinity, with a metric, a flat metric ds squared equals dz bar. So by definition, a conformal transformation is a transformation that preserves angles. So if I have a function f of z, well, let's assume f is holomorphic. Then the metric transforms into f prime of z modulo squared dz bar. So the metric only picks overall scalar factors. And this means that my transformation preserves angle. And that's why we have an infinite dimensional symmetry algebra, because the space of holomorphic functions is infinite dimensional. So what is this this algebra? Well, in fact, there is a small subtlety, which is that I want to consider holomorphic functions, but not necessarily on the whole Riemann sphere, but only on C star, so which is the Riemann sphere minus 0 and infinity. And the reason for that is basically that I want my conformal transformations to act on the space of states of some theory. And the space of states will live on, let's say, some circle here, maybe the circle z equals 1, which you can view as a Euclidean time slice of that Euclidean two-dimensional space. And holomorphic functions on near this circle, well, that's equivalent to holomorphic functions of the whole sphere minus the 2 points. So let's consider infinitesimal conformal transformations. Then they are generated by differential operators ln minus z to the n plus 1 z by dz. So ln is in general not holomorphic on the whole sphere. It can have singularities at 0 and infinity. But that's really the algebra of local conformal transformation. So which algebra? Well, it's a Lie algebra whose commutation relations are ln lm equals n minus m ln plus m, and it's called the Lie algebra. So particular generators include L minus 1, which is minus d by dz, and which generates translations, or L0, which is minus z d by dz, and which generates dilations. In fact, we have a SL2 subalgebra generated by L minus 1, L0, L1. And this is the algebra of global conformal transformations, the ones that exist not only on C star, but on the whole sphere. And one way to see that is to exponentiate them, and instead of infinitesimal transformations, I could consider well, finite transformations. So if you exponentiate these generators, L0, L1, L minus 1, you get transformations of the type Z goes to AZ plus B over CZ plus D with AZ minus BC not 0. So if you want, this gives you the group of global transformations of the sphere, which is PSL2C. So it includes well, translations, dilations, and more. Okay, are there questions on this? On this, let's say, geometrical part. So now, I mean, yes?
So there are other SL2s. If I take like L2, L-2, and L0, I rescale generators, that makes a different SL2. Are these everybody's?
Yeah,
but it's not related to global.
SL2 algebra, that's all I'm saying. Is it significant size?
yeah, I think I totally agree with Michel's answer. You can find other SL2s, but this one is the one which has a geometrical interpretation. In the same way as in some CFTs, you can find several Virasoro algebras, but only one of them will correspond to conformal transformations.
In fact, you can be even more pervert somehow. If you just take the odd or only the even LNs, you make another Witt algebra if you rescale correctly. So the Witt algebra contains a subalgebra, which is again a Witt algebra, and you can, but only that one is meaningful.
Yeah, so we are still stuck with the Witt algebra. So why did I say that you needed a Virasoro algebra? Well, that's for a general reason in quantum theory, that basically your geometric algebra here has to act projectively on states. And a projective action of an algebra is the same as an action of a centrally extended algebra. So that's why you always have to look for central extensions. And so if you look for central extensions of this Witt algebra, you find basically unique. So it's called the Virasoro algebra. It has generated big ln, which correspond to the small ln. And so the permutation relations are, well, they start the same. But then you have an extra central term, which is C over 12 n squared minus 1 delta n plus m 0. C here is a parameter called the central charge. So let's say a complex parameter. So it's a nice exercise to show that this is the only possible extension such that you still have a Lie algebra. So this central charge is an essential parameter, not only for the algebra, but for any conformal field theory. In fact, in my introduction, I already mentioned that, well, it had a physical interpretation when you wanted to apply it to gravity, and that the properties of the CFTs would depend a lot on the value of this central charge. Okay. So we have our algebra. Next, we have to look for its representations. And, well, the reason is that, of course, the space of states of our conformal field theory has to be a representation of the Virasoro algebra. But which types of representation we want? Well, the idea is that we want representations, we want to look at the eigenvalues of the L0 generator. And the physical reason is that we want to interpret L0 as the Hamiltonian, and its eigenvalues are the energies. And in physics, you want the energies to be bounded from below, otherwise your system is unstable. So that would be the condition. Actually, when we compute operator product expansions, we'll see that having eigenvalues bounded from below is necessary for the operator product to converge, and that would be a technical motivation.
But you want L0 to be Hermitian, L0 dagger.
No, I don't want L0 to be Hermitian.
But you want real eigenvalue.
No, not necessarily. I don't necessarily want real eigenvalues. Yeah, it's better to have things remaining analytic as long as we can.
Could you repeat what you said about the OP convergence?
Yeah, so if your LDO was not bounded from below, then it would be very hard to make OPs converge.
What do you mean by bounded below is the real part?
Yeah, right. Thank you. So bounded from below means in real parts, since I'm not assuming them to be real. So let's call an L0 eigenvalue, let's call that a conformal dimension. So let's say we have a vector V, which is an eigenvector of L0. So delta is called the conformal dimension. So let's see how this conformal dimension behaves when I act on V with some Virasoro generated Ln. So first, technical exercise, hopefully not excessively difficult. So let's write that as L0 Ln commutator V plus Ln L0 V. So L0 Ln, using the Virasoro algebra commutation relations, that's minus N Ln V. And L0V is delta V by assumption, so plus delta Ln V, which is delta minus N Ln V. There is a V here. So the outcome of this small calculation is that acting with Ln decreases the conformal dimension by N. Now, if we start with some eigenvector and we act with Ln and decrease in conformal dimension, well, we will have to stop at some point because we want it to be bounded from below. So more specifically, let's consider eigenvector V with the smallest dimension delta. Then, if we add with the Ln strictly positive, well, what do we find? Well, we have to find 0. Otherwise, we would get a state with an even lower dimension. So, these two conditions are the definition of a primary state. Then, if we have a primary state, conversely, we could act with N negative, and then we could build other states which don't have a particular reason to vanish. More specifically, let me introduce some basis of creation operators L. So L is just, well, 1, L minus 1, L minus 1 squared, L minus 2, etc. So let me describe it as products of L minus Ni from I equals 1 to k, such that, well, N1 is strictly positive, and then they are ordered. N1 less than N2, etc., less than Nk. So that's what I call the basis of creation operators. And for any element of that basis, so some L in big L, I have LV, which is a descendant state. Well, I'm calling it a descendant state of the primary state V. Or also a linear combination of descendant states is also a descendant state. It's for all k. Yeah, k belongs to, well, it can even be 0, in which case I get the 1 here. It's for all positive integer k. Okay, so now we could consider. Yes?
Can you think about the boundedness of L0 again?
Yes.
So, for strictly infinite central charge, the the radius of convergence is 0, because L0 is minus c over 12. The ground state is minus c over 12, which is in minus infinity. And is it that the the radius of convergence is 0?
Yeah, I'm not sure about infinite central charge. It probably depends which spectrum you take, in fact. Yes?
I finished. Yeah. You didn't mention it, but I guess you don't ask L0 to be diagonalizable, do you?
Not yet. Well, in fact, if you want to do loop models, it's not diagonalizable in general. But with yeah.
But you make some. If it's not diagonalizable, then if you want to split your space into pieces, what are the conditions you ask on the different pieces?
Yeah, so I'm asking that the space of states can be decomposed into indecomposable representations. I think that's a rather mild assumption.
Sorry, just a small comment on the previous question about infinite sample charge. So basically, we measure energies with respect to the vacuum state. So it might be that you have, the vacuum to be infinite, but you measure all your states with respect to that. So you might have finite energies. In some, okay, I don't know how you want to take a large sample charge limit.
The gap is always difference of the energies are always finite.
Yeah,
and that's what goes into the OP convergence calculation.
Yeah. I mean, depends how you take this large sample charge limit, but
okay.
Okay, so if we start from a primary state V and we consider all the LV, or rather the span of all these LVs, of all the dissonant states, for L belonging to our basis curve L, then, well, this is by definition some representation of the Virasoro algebra, which I can write RV. So now we want to consider the structure of this representation. So one possibility is that these states are all linearly independent. So if they are linearly independent, then by definition, RV is a Verma module, which I can write V index delta. Well, if they are not linearly independent, it means that this RV has some, well, is smaller than the Verma module. So in fact, it will be a Verma module divided by some sub-representation. But in both cases, I mean, these are all representations we call highest weight representation. And in such representations, L0 is diagonalizable because we built them from a primary state. So let me draw a bit more precisely the structure of a Verma module. So to do that, I introduce a convenient notation. I'm calling N or L. I would call that the level of the dissonant state LV. For example, the level of L minus 3, L minus 2 squared, that would be 7. Sorry, I did not give you the definition, but maybe you get the definition from this example. So the level is sum of Ni, where the Ni here are the indices of this Virasoro generators. So if you want to draw a Verma module, we start with the primary state, which by definition has level 0. And then we can build the other states using creation operators. So if I use L minus 1, I get L minus 1V, which is the only state at level 1. Now, if I act again with L minus 1, I get L minus squared V at level 2, but at level 2 I also have L minus 2V. And then I can go on. At level 3, I have L minus cube V. I have L minus 1, L minus 2 V. And I also have L minus 3 V. So that's the level 3. And this goes on forever. And that's your Verma module. So we have one state at level 1, two states at level 2, three states at level 3, and how many at level 4? Well, we have 5, in fact. Okay. So that's all we need to know on Verma modules, but, well, not quite. We also want to know if they are irreducible. So we want to understand the structure in a bit more detail. Because if they are not irreducible, it means we have sub-representations and we can build other representations by taking quotients. So we want to know, in fact, if they are irreducible. So to know that, let me define the concept of a null vector or singular vector. By definition, this is a descendant of some primary state. So a descendant that is also primary. And the point is that if you have a sub-representation, so if we start with a Verma module, let's say, generated by some primary state V, and if you have a submodule, then you can look in this submodule at the state with the lowest dimension, and this has to be a null vector. So if you, let me call it, let's say, W, a submodule. So the state X in W with lowest dimension. Well, since W is a submodule, it is a descendant of V, but since it's the lowest, the state with lowest dimension of submodule, it is itself primary. So this X is prime is a null vector. And therefore, the Verma module is irreducible if and only if there are no null vectors in that module. Okay, do you agree with this algebraic statements? So if you agree with the principle, well, we have to put it in practice and actually look for null vectors. So where could we find null vectors in a Verma module? Well, let's start with level 1. So is there a null vector at level 1? So null vectors. So is L minus 1V a null vector for V some primary state of dimension delta? So to know that, I have to know if it's primary. Well, fortunately, the definition of a primary state is already there. It's a state that's an eigenvector. Well, that's already an eigenvector of L0, but also it has to be killed by the annihilation modes. So I have to compute ln L minus 1V. Well, that's the commutator ln L minus 1V. here I'm assuming n is positive. So ln kills v because v itself is primary. And this commutator is n plus 1 ln minus 1v. Well, if n is 2 or more, that's 0 because v itself is a primary. But if n equals 1, I get 2 L0v, which is 2 delta v. So that let me write this. L1 acting on L minus 1v is 2 delta v, and that is 0 if and only if delta is 0. So therefore, we have a null vector at level 1 if and only if the conformal dimension delta is 0. So this tells me in particular that the Verma module of conformal dimension 0 is reducible. We already know that it has a submodule which is V1, the Verma module of conformal dimension 1, which is generated by this L minus 1V. Okay? So next, let's do level 2. So you may be frightened. I mean, at which level will I stop? 5, 6, maybe. Well, I promise level 2 is the last one, and I won't even do all the calculations by hand. But in principle, if we want to know if our module is reducible, we have to do all levels. But fortunately, we don't have to do that by hand. So level 2. So at level 2, let me write the generic descendant state as follows. So a L minus 1 squared L minus 1 squared plus a L minus 2 L minus 2 acting on V. So V is my primary, and I act on it with some combination of L minus 1 squared and L minus 2 with some coefficients A here. Okay, so this is a null vector if and only if two conditions are fulfilled. L1 is 0 and L2 is 0. Well, only two conditions, because if I act with L3, well, since V is primary, automatically I would get 0, because L3 brings me 3 steps higher, so I just fall out of my representation. And so we have to compute this L1x and this L2x, and the answer, well, let me cheat a bit and copy the notes. So that's 4 delta plus 2 a L minus 1 squared plus 3 a L minus 2 L minus 1v, and L2x is 6 delta a L minus 1 squared plus 4 delta plus c over 2 v. So hitting the L minus 2 here, so we needed the commutation relation of L2 with L minus 2, which, well, unfortunately I have erased the Virasoro algebra, so what a tragedy. The Virasoro algebra contained, well, let me write it again, ln equals n minus n ln plus m, a central term c over 12 n squared minus 1 delta n plus m 0. So this central term has the good taste to vanish if n is 0 or 1, which means that my SL2 subalgebra of global conformal transformations doesn't have a central extension. But for n equals 2, this central term no longer vanishes. And, well, if you put 2 here, you'll get 6 over 12, you get 1/2, and this is, well, this is the c over 2 you have here, basically.
In the term that contains the c, is it multiplied by a L minus 2 equation, I guess?
Right, thank you. We had a L minus 2 here. So if we want a null vector, these two numbers, in fact, have to vanish, which means that AL-1 squared and AL-2 have to obey a linear system of two equations. And for a solution to exist, the determinant of this system must vanish. And the determinant of this system is a combination of delta and C, so we get a constraint on delta, but now instead of some simple solution like delta equals 0, we'll get a delta which depends on the central charge C. And what is this delta? Well, there are two solutions. I mean, obviously, that would give me an equation of a polynomial of order 2 in delta. And the solutions are delta equals 1/16 5 minus C plus or minus square root C minus 1, C minus 25. So delta belongs to these values is equivalent to V delta having a null vector at level 2. So now you may start to worry that things are becoming a bit complicated. What happens if I go to higher level? Will I get ever more complicated formulas? Well, in fact, it doesn't get much more complicated than that, essentially. Still, I find it a bit too complicated for the moment. I mean, first, it's not analytic, it has a square root. And anyway, I mean, if we start to tolerate square roots this early, I mean, we are cooked. I mean, later we have double Gara functions, stuff like that. I mean, we don't want to have already square roots. So let's eliminate this square root. And, well, the one way to do that is to change notations. Yeah, I'm concluding that C is not a good parameter. The representation theory of the Virasoro algebra doesn't like C. It prefers a parameter which I will call beta, such that C is 1 minus 6 beta minus 1 squared. And if you rewrite this formula in terms of beta, it amounts to delta equals minus 1/2 plus 3/4 beta plus or minus 2. So our two solutions have become a bit simpler. Yeah, of course, I mean, this change of notation is not completely free. The problem is that it introduces ambiguities, meaning that C is invariant when the beta goes to minus beta or beta goes to 1 over beta. So we'll have to remember these ambiguities, but that's a price we want to pay. Okay. So then, what about the null vectors at all levels? Well, now there's a statement which I won't through right now, which is that there is a family dimension called delta Rs for R and S positive integers, such that the Verma module V delta Rs has a null vector at level R times F. So this null vector, let me call it L Rs V. V now straight V is my primary state V delta Rs. And well, first of all, let me show that the results at level 1 and 2 fit into this pattern. So let me do some table with these results. No, I mean, this is true for arbitrary beta.
No, yeah, but for a given beta, there's only null vector at a given level.
For if you fix R and S, a pair of integer indices, then yeah, you have a null vector at this level R times S. But if you want to look at a given level, you have to look at how you factorize it into two integers, R and S. So that's what I'm doing here for the first level. So first level is 1. Well, I don't have much choice. R and S has to be 1, 1. And then what is delta Rs? well, we computed it, we found it was 0. And then what is the LRS, the creation operator, which gives me my null vector? It's just L minus 1. L minus 1. So at level 2 now, well, we found two possibilities, two values of delta, and well, 2 has indeed two factorization, 1 times 2 and 2 times 1. So I have 2, 1 and 1, 2. The deltas are well, minus 1/2 plus 3/4 beta squared and minus 1/2 plus 3/4 beta minus 2. And if we had done the calculation, if we had solved actually this linear system, we would have found the LRS to be L minus 1 squared minus beta squared L minus 2 and L minus 1 squared minus beta minus 2 L minus 2. So, what about higher levels? Well, again, I want to simplify formulas by introducing another notation. No, it's not a notation for the symplecon, it's notation for delta. Okay, we can say that this delta here is simple enough, but I want to make it even simpler. And to do that, we introduce the momentum P, such that delta is C minus 1 over 24 plus P squared. And then the claim is that the dimension delta Rs corresponds to the momentum PRS, which is just 1/2 of R beta minus S beta minus 1. So this is the dimension of, well, the momentum of a primary state which has a null vector at level R times S. So that's a very important formula. In fact, we use this formula as a convenient notation even if R and S are not strictly positive integers. So now you can ask me, what is the null vector itself? What is the LRS? And, well, that's really complicated now, and actually not very useful. So I don't want to say what is LRS, but there are interesting works on that subject.
Is the ordinal vectors in the ordinal table?
No, not always, in fact. So let me, I will.
Sorry, wouldn't you prefer to have C minus 1 divided by 12?
No, I mean here delta is the chiral dimension. It's if you have the total dimension is delta plus delta left plus delta right, and that one is.
It's just because I would like to find delta equals 0 when I plug in. Or because C minus 1 divided by 24, I would see 1/4.
Okay, so let's check indeed that delta 1, you want delta 1 to be 0, right?
Yes.
So C minus 1 over 24, here C is like that, so I get minus 6 beta, sorry, 6 is divided by 24, so 1 minus 1/4 beta minus 1 squared, plus P squared, P. So for
P squared, I'm sorry. Yeah, that's fine. Okay, perfect.
Yeah, so I think there is no mistake for the moment. Not yet. But you're right to keep your eyes open. Okay, so yeah, so the dynamics question was indeed very important, and you asked this, the only null vectors. Before answering that, I have an important remark to make on these values of delta Rs, which is if you compute now, if you want to compute the conformal dimension of your null vector, so this null vector here, well, you start with the dimension delta Rs of the primary state, and you add the level R times S of the null vector, and that gives you the conformal dimension of the null vector, and the point is that it can be rewritten as delta R minus S. Of course, its indices here are no longer positive, but still they are of the type delta Rs. Okay, so now if we have a Verma module, what are all its null vectors? Here the situation depends on the value of beta squared, or equivalently of the central charge. So if you wanted to have two different null vectors of that type, you would need to have an identity of the type delta R1S1 equals delta R2S2. Right? If you want two different null vectors. So that identity implies there are two null vectors. But if you have such an identity, I mean, both these numbers are functions of beta, and their coincidence means you have a constraint on beta. And in fact, this implies beta squared rational. So therefore, the first and the simplest case is irrational. So let me assume beta squared is a complex number, but not rational. Well, in terms of the central charge, it corresponds basically to generic values of the central charge. And then the statement is that the number of null vectors in a Verma module such as V delta S has to be 1. So in this case, basically a Verma module has a null vector if and only if delta is of the type delta RS, but it has only one null vector.
Just to be clear, at this point we don't really know that delta RS is a proper null vector, right? We have checked it for delta 1, 1, delta 1, 2 to 1. But how do we know that for a larger RS, this formula will give us our null vector?
Yeah, well, that's a claim. That's a claim which is not proved. I mean, there is a way to derive this PRS by doing OPs, essentially. So you start with non-vectors at level 2, and you do OPs with one another, and you generate all the others. But we are not yet doing OPs, so for the moment, it's an unproven claim.
You also claim that these are the only.
Well, for this beta squared, they are the only ones. They are not the only ones in general.
No, you're claiming that all the null vectors have dimension delta of this.
No, I'm not claiming that.
For this argument here, you used it because you said you need a coincidence between these two.
Well, but what I wrote is a bit more precise than what I said. I mean, here I said this implies beta squared is irrational. I mean, I didn't say I need. Okay. I didn't write the implications in an equivalence.
By the number of null vectors being 1, in this case, a little bit confused. Maybe at level 2 we saw that we have two null vectors like the delta 1, 2 and the delta 2, 1. So okay, yeah, module of this.
No, here I'm focusing on one particular dimension. For example, delta 2, 1.
Okay.
So if you fix your dimension to be delta 2, 1, then you have one null vector. If you wanted to look at the other null vector, you would have to look at a different Verma module with another dimension.
Okay.
Yeah, so sorry for the confusion, but here we are looking at one Verma module, and we want to find all null vector in that Verma. Then it's not only beta being rational which matters, but it will be also the sign of beta. And to see that, let's consider beta squared rational now, Q over P. And if you look at this formula for delta RS here, you will realize there is an identity delta R plus P S plus Q is also delta RS. So if I start with some delta RS, in principle, I could generate other deltas, other than vectors by just shifting my indices, provided they remain positive. So that's where I need to worry about the sign of these numbers. So the first case is when beta squared is positive. So in this case, I can assume P and Q positive. And then if I start with a null vector, a Verma module with a null vector of dimension delta S, then I have in fact infinitely many other null vectors, because whenever I shift R and S by P and Q, I get another null vector.
So, are these statements about a number of null vectors, do they only apply, like, are you only counting null vectors which are not themselves descendants of other null vectors by any chance? Because like if I take the case of generic beta, so beta irrational, I said delta to 0, then by previous argument we saw we have a null vector at level 1, which is L minus 1. But then at level 2 there is a vector L minus 1 squared v, which I think is also a null vector.
Right. No, but a null vector by definition is primary. So you L minus squared v is a descendant of the original null vector, but it's not primary. It's not itself a null vector. So you should view it like any sub-representation corresponds to just one null vector.
So you're saying that if I hit the L minus 1 squared with some positive Ln, then it's not going to vanish?
Right. Well, let's draw it here. So you start.
Sorry. You're right. If I.
So here you have a.
No, I screwed up.
Right. So
with the L1, then
yeah,
you get something positive.
So yeah, for the others maybe I'll explain this point a bit more carefully. So we start with a Verma module of dimension 0. So indeed, in that Verma module, I have a descendant L minus 1 V0, which is a null vector at level 1. So it itself has dimension 1. I can call it V1. It's a primary field of dimension 1. Then I can act again with L minus 1 on this thing. But I mean, the vector I obtain is just not a null vector because it's not primary.
It's not a primary, because if you apply L1 to it, you don't get 0.
Yeah. If I apply L1, I go back to V1 because now I'm in a Verma module of dimension 1, not 0.
I want to insist a little bit on the rationals here. So these are rationals in real, right? Not like complex numbers that have irrational imaginary part and rational real part. Well, what happens in this case? This falls into your first category, the generic?
Well, I mean, generic means anything except rational.
Like real.
Indeed, rational means real.
Real. Okay. But nothing special happens when I take imaginary parts to also irrational?
No, not at all. I mean, you can view it by doing this small calculation. You assume two of these numbers are equal and you get a real rational number. Okay, so as I just showed, if C is of this type, then we always have infinitely many null vectors in any of these modules, and they are not even all of this form, delta S. In addition, you can have others which are not of this form. I won't get into these details. And for, well, okay, central charges here means are all less than 1, and they are rational as well. Now, if Q is less than 0, and that's probably my last statement before the break, so then that corresponds to 3 greater than 25. And we always have a finite number of null vectors. So if we want to use this argument, for example, we have P, let's say, positive and Q negative. So you see that if you start to shift the indices R and S, at some point one of them will become negative and it won't generate a null vector anymore. And another way to see that you have finitely many null vectors is that the set of conformal dimensions here, delta RS of degenerate dimensions, well, for Q, for beta squared negative, it is bounded from above. For beta squared negative. By some bound A. So you can just deduce it from these formulas. And
so what is A? Is it complex?
No, A, I mean, we can compute it. It's just the maximum of all these numbers when you vary R and S over integrals. It's, well, okay, less than, in real part, of course, I mean. Less than A, some bound A. But whenever you have a null vector, of course, by definition, it has a larger dimension than its primary state. And so, if you increase the dimension, well, you hit the bound, and then you can't have any more null vectors, basically, because you can't have any more dimensions of this type delta RS. Although I considered that not all null vectors are not of this type. Okay, so that's all for the before the break. Now, the conclusion of that is that life is much easier for generic single charge.
I guess part of the sort of discussion we were having before is due to this linguistic turn that a null vector is not the same thing as a vector that is null, in the sense of having a zero norm. It's more than that.
Yeah, okay, so after the break, I will do a hair splitting along this line. So we'll introduce null vectors that vanish and null vectors that don't vanish. And I think that will answer this type of questions.
Null, because when you quotient, you nullify these vectors and their descendant.
Yeah, right. But I have the choice of either quotienting or not. So that allows us to build different representations.
I guess the important point is that up to now we haven't introduced any inner product at all. All of this was completely independent of any notion of inner product.
Right, and we will never introduce any inner product, in fact.
Because we don't need it?
Right, we don't need it. That's not very useful notion.
There is one, right? We don't have a Hilbert space, so.
Well, you don't generally have a Hilbert space. To have a Hilbert space, you need to take a lot of constraints, including having the central charge real to start with. I mean, you can show that if you assume that your L0 is self-adjoint, I mean, that has to imply central charge is real, for example. But that's only the beginning of your trouble. I mean, you have other constraints as well, including on the conformal dimension. So we won't get into that.
But if you're in that realm, it does make something simpler. Like some of these null vector regulations can be put into the product in some way, which is maybe slightly quicker.
Okay, so that's now the big challenge for the rest of the course. So I will be giving derivations of various results, and if you can find a simpler derivation using a scalar product, then well done.
So at some point earlier during the lecture, somebody brought up the case when L0 may not be diagonalizable. I didn't quite understand whether all of what you said still applies in that case, or whether there are some modifications that need to be done.
So, right, so I have been focusing on Zerma modules, where by definition L0 is diagonalizable, and also on highest weight representations, which are quotients of Zerma module, where L0 is still diagonalizable. So I'm not looking at these cases now. These cases are, in principle, the subject of section 6 of the lectures, which we don't have time to deal with.
I can read them.
Well, but they are not written yet either.
Read them in the future.
Yeah, in the future. Yes.
This is more simple. Does this capital A depend on C?
Yeah. So probably we can just compute it right now. So this capital A, I mean, you see beta squared now is negative. So this PRS squared is also negative. So this capital A probably is just C minus 1 over 24.
Can you clarify again the status of what's proven about null vector formula?
You mean the formula for the explicit null vectors here?
Yes, so the PRS, the extent to which these are or are not all null vectors at all levels. What was the claim?
So let me make a more precise claim then. So we are in one of these situations when we have several null vectors. So the claim is that all null vectors are of the type where some L R1 S1 V or L R1 S1 L R2 S2 V. So you have these null vectors of null vectors which are not of this type. But it stops here, meaning if you were tempted to look at something like LR1 S1, LR2 S2, L R3 S3 V, then you can always rewrite that as some L R4 S4 V. And in fact, it's an exercise to check that at least this works at the level of conformal dimensions. You can rewrite the conformal dimension of this null vector in this way. So that's the statement, basically.
It's a claim or it's proven or
Yeah, it's probably proven. I mean, by like works, I think. Well, I guess by Fagin and company in the 80s.
So in CFT literature, people introduce this catch determinant. What you are doing is analogous to that. I mean, all these formulas can be derived from the catch determinant. Are you doing? I mean, doing a like a similar treatment? It's an equivalent thing that people do in
Right. So the catch determinant is one way to derive these indeed these formulas, but I will derive them in a different way using.
Yes, so I'm asking like what is the difference in assumptions between the usual catch treatment of the catch determinant?
Well, to write your catch determinant, this is the determinant of a so-called gram matrix of scalar product. So you need to introduce a scalar product. So I guess the difference is that I don't introduce.
You didn't introduce a scalar product.
But the price I pay for that is that my proof will rely on fields and operator products. So I can't do it just at this algebraic level.
And you do not require hermiticity of L0.
No, I never require that.
Everything that has been said here is also true for complexes.
Yeah. Should I start again? Not yet.
The coffee is slow, so I know, but everybody.
Everyone is back from the Can plug it in.
You don't need a pen?
No, I don't.
Okay, let's go. So now I want to talk about what we do with null vectors when they exist. So let's assume we have a representation RV which is generated by V, the primary state. And let's assume we have some null vector in that representation. So that's a null vector. So then what we can do is to generate from this null vector, which I can call x, we generate a representation by acting with all the creation operators. So that's our x, which is a sub-representation. And then I could define a representation, a new representation, RV quotient Rx. And in that representation, by definition, the null vector LV vanishes. So I would say this representation has a vanishing null vector, which on the face of it is a pretty nonsensical statement. It means it has a vector which is 0. But what I really mean is that the primary state V, which generates the representation, obeys this equation. And that's a really non-trivial statement. So this is a null vector equation. So on the other hand, the representation RV itself, well, it has a non-vanishing null vector. Because so long as I don't take the quotient, this LV, this null vector, well, doesn't vanish.
Well, that's if you start with the Verma module. If you start with the representation you've already taken the quotient of.
Yeah, well, by vanishing, I mean vanishing inside this representation here, RV. When I say that there exists a null vector in that representation, I mean, I don't mean there exists a 0 vector in that representation. Okay, null vector is non-zero by definition. I mean, it's just a matter of terminology here. Now, if there exist several null vectors in the same representation, then for each null vector, basically, I can decide whether I want to quotient or not. Well, except if a null vector is a null vector for another null vector, then if the first is 0, then the descendants have to be 0 as well. But in general, I can have several possibilities. So let me define a degenerate representation as a representation which has vanishing null vectors. Let me define a fully degenerate representation as a representation where all null vectors vanish. Right? Then, what is the structure of such representations? So, for example, let's consider a Verma module V with the dimension of the type delta Rs. So it has a null vector. And then I can define a degenerate representation, which I will call RD for degenerate Rs, as the quotient of that with the sub-Verma module generated by the null vector. And, well, if beta squared is not rational, then this RD is also fully degenerate because there is only one null vector anyway. So I can write it RF, RS, F for fully degenerate. On the other hand, if beta squared is rational, you can have several null vectors. So what is the structure then of the fully degenerate representation? Well, the statement is that it's always enough to set two null vectors to 0. So the fully degenerate representation is always of the type Verma module divided by a sum, not a direct sum, of two submodules. So these are Verma modules, and they're all generated, I mean, they're highest representations, so they're all generated. So I want to introduce notations for the degenerate primary fields. So a degenerate primary field, VDS, is a field that obeys the null vector equation. And I also have the notion of a fully degenerate primary field. And you should not confuse it with the field V delta RS, which generates a Verma module and which is not degenerate. And in particular, this one does not obey a nil vector equation, although it has exactly the same conformal dimension as the degenerate primary. Okay, and that is all I want to say on representations of the Virasoro algebra. So we are done with algebra, basically, so we will be able to do field theory now. Other questions? So, no questions. Let's do field theory. So that's in the notes, section 1.2, field and operator product expansions. So, well, the fundamental object of field theory are fields. And what are fields? Well, there is a correspondence between states and fields. I mean, this correspondence exists in general quantum field theory because you can act on the vacuum state with a field and you get some other state. The point is that in conformal field theory, this correspondence is a bijection. So the space of states is the same, basically, as the space of fields. So that's what we call the spectrum. Let's say it's an axiom which has a good physical motivation. The idea is that, let's say you have a field at this, and in general you would change that state by bringing it close to that field. So let's say by shrinking the circle to small size. But this operation in general is kind of irreversible. You're taking a limit. But if you're in CFT, small size and large size are the same, basically, because of scale invariance. So you don't expect to lose any information when you do this type of operations, and that's why you would assume that it's a bijection.
So this argument seems to hold for any critical theory.
Right. So
even in 4 dimensions or whatever.
Yes, right. Right, you don't really need the full conformal invariance to make this. Sorry. Okay, so now we have a bijection, then everything we know about states, we also know about fields. In particular, we have primary field, we have degenerate fields, non-degenerate fields, we have descendant fields, etc. So what we are doing is that we are taking a state and we are assuming it depends on z, on the position on our sphere, and then it becomes a field. So of course, I mean, I'm not just decorating states with some extra z. I want to say something about the dependence on z. So that will be our first axiom, basically. On the other hand, what I won't do is to try to construct fields. I mean, we are in an axiomatic approach, so I'll define fields by the axioms they obey. And in fact, fields are not really the observables. The observables will be correlation functions. So you can view these fields are just a convenient notation for making statements about correlation functions. Okay, so what's the first thing? Well, the first thing is we want to determine how the fields depend on z. And the axiom is that d by dz of z is n-1 d of z. So, of course, since I have a bijection between states and fields, the Virasoro algebra also acts on fields. So that equation makes sense and determines how fields depend on z. It also makes intuitive sense because originally in the Vit algebra, the -1 generator was the generator of translations, and that's precisely about translation.
Is it intentional that now there is no minus sign in front of the d by dz? The different algebra there was a minus sign.
Yeah, right, it's intentional. Yeah. Okay, so now let's draw some consequences of this axiom. So this axiom is supposed to assume to really any field. So in particular, if I act on a field with ln, I get another field which is also supposed to obey the same axiom. And now to be clear, let me add extra label z to ln. Because this Virasoro generator, well, they can act at on any field at any position, but this makes them depend on z. So I'm making this dependence explicit here. And from this axiom, we will be able to derive how ln depends on z. Because we are computing this by, well, that's d by dz ln of z, d of z, right? Plus ln d by dz d of z, which is equal to, well, n minus 1 against d of z. So now the point is to apply the same axiom to this v, or to this original v. And what I get by doing that is the relation d by dz ln z equals L minus 1 ln z, right? And since this is true for any field, I can write that as a relation for just the Virasoro generators, ln z. And now I can use the commutation relations of the Virasoro algebra, and that gives me minus n plus 1 ln minus 1 z. So we know how these generators depend on z. Okay, any questions, or do you feel that I'm cheating somehow? I mean, it's really just the consequence of the axiom. Okay, so now the idea is that we have here an infinite number of relations. That's true for any n. And we want to write a generating function. So the way to do that is to write this as to sum for n belonging to z, ln z over y minus z n plus 2 equals 0. So I'm claiming that this infinite number of equations is equivalent to this one, where I have introduced an auxiliary variable y. And now I want to define this object as t of y. Since it doesn't depend on z, I can call it t of y. That's the energy momentum tensor. And in particular, this t of y, by definition, obeys, well, t of y v of v for any field is just describes how all Virasoro generators act on that field. Sum ln, well, ln v over y minus z n plus 2. And conversely, if I know this t of y, I can recover ln v of z as the contour integral along z of dy y minus z n plus 1 t of y v of z. So this energy momentum tensor, let's view it as a really convenient technical object, which will simplify a number of calculations. I don't want to make a deep statement about it belonging or not to the spectrum of the CFT, in fact. So let's write this equation in the case of a primary field. So, well, yeah, the definition apparently depends on z, but then
the same way as the L.
Well, no, but the L's really depend on z, but the t itself, we have shown that its z derivative is 0. So in fact, it doesn't depend on z. Well, we have constructed it in order that it does not depend on z. So now, if my field v delta of z is primary, then let's write this relation for this field. So T of y, V delta of z. I have in principle I have to sum over all integers n, but since the field is primary, it's killed by ln with an n strictly positive. So this formula will start with the case n equals 0. I will have L0 V delta, which is delta of V over y minus z squared. The next term is L minus 1, acting on V delta, which I can write as V by dV, V delta over y minus z. And the other terms, when they are regular, as y goes to z. So let's write it as O of 1. So this we will shortly interpret as an operator product expansion of the energy momentum tensor, which we want to view as a field, in fact, with a primary field. And this is equivalent to saying that V is primary. So in principle, I can now forget about the Virasoro algebra, and all I want to say about conformal symmetry will be encoded in the properties of this T, of this energy momentum tensor. So now let's make really the strong axioms that will allow us to solve the CFT, starting with the existence of operator product extensions. And here we've seen, if you want an example, but the axiom is that for any two fields, so V1, Z1, V2, Z2, the product of these fields is in fact a linear combination of fields. So there is a sum over k of some coefficient here, C1 to k, which depends on V1, Z2, Vk at Z2. So the sum is over all fields, a priori. Okay, so that's the most important axiom of conformal symmetry. It's the axiom which leads to the bootstrap, to crossing symmetry. So I'm just introducing here this C, which is just a number. So they are called OPE coefficients.
If I want to, so you have this expansion here on the left corner.
This one?
Yeah. I cannot replace this V by T, right? Because then I will get the wrong TTOPE. What exactly is breaking down?
No, you get the right TTOP if you do that.
Then you get the right OPE?
Yeah. Don't forget that T is not primary. If you want all the terms, you have to take that into account.
Yeah, but okay. So if I will get the right OPE. Okay. It's just that I will have the fourth order pole.
But maybe since you asked the question, maybe I can write it now. So if you do P of y, P of z, well, according to the general formula, you should get, well, let me write only the terms which are actually non-zero. So you have L2t of z over y minus z fourth, plus L1t of z, but that term will end up being 0, plus 2t of z over y minus z squared, plus dt over y minus z plus order 1. So, in fact, this term happens to vanish. And in fact, this L2t happens to be equal to C over 2. And that's your T of T with itself. And again, in the same way as this OP with a primary field is equivalent to stating that this is a primary field, the OP of T with itself is equivalent to the commutation relations of the Virasoro algebra. So that's a nice exercise, but again, it illustrates the point that once you have T, you don't need the Virasoro algebra anymore.
I didn't quite understand if you're trying to make a distinction between the space of fields and the vector space of states on S1, or is it even important that we are identifying the space of field with some space of states on S1, or?
Yeah, I think it's important. it allows us not to introduce two notations for the same thing, first of all. And then it also says that we can recover all information about fields. And if we know the space of states, we know all the fields already. So for example, when you do an OPE of two fields, you have a sum here, and the sum is over all fields, which means over all states, in fact. You don't have extra stuff to sum over.
I'm partly asking because somebody made a comment that it doesn't matter whether we think of T as being in the spectrum. So I guess what do you mean by the spectrum? Is spectrum the whatever appears in the vector space on S1?
Yeah, so the spectrum is a tricky notion, I would say, which I will discuss more in the probably next lecture. So the idea is, I will distinguish spectrum with extended spectrum. Extended spectrum is whatever you can add without making the CFT inconsistent. So typically in a CFT like in Liouville theory, I want to consider T, then the tensor as not part of the spectrum, but part of an extended spectrum. So, which means that I can always add T in correlation functions, that's consistent. But if I do an OPE, T will not appear.
Does it mean that there is no state? I guess it would be a situation when there is like no usual vacuum in the.
Right. So in Liouville theory, you can do away with the vacuum state. It's not part of the spectrum, and you have a consistent CFT.
This is at the order of the Lie algebra, because you could be a bit more ambitious and ask how operators transform under a general conformal transformation.
You mean you want not just infinitesimal conformal transformation? Indeed, T generates this infinitesimal transformation. You want the global conformal transformation. Yeah, well, that's a bit more tricky, but yeah, you can do it, but typically not on the full sphere. So if you want a globally defined conformal transformation, typically you want to have an open domain. Because on the full sphere, we know the global conformal transformations. Well, it's only a three-dimensional group, PSL2C. Okay, so we have just introduced operator product expansions here. So again, operator product expansions, they can exist in general quantum field theories, but they would exist only in an asymptotic sense when Z1 is close to Z2, when Z1 goes to Z2, in fact. In conformal field theory, what happens is that this is supposed to be true in a finite neighborhood of Z. Let me call it ZZ2, maybe a small disk around Z2. And so in this small disk, it's supposed to be a convergent sum, which allows you to exactly compute this product of fields. And that's why you can have this bootstrap technique, in fact. Okay, so there are other assumptions. In particular, fields commute. V1, V1, V2, V2 equals V2, V2, V1, V1. Well, it's a kind of triviality because, well, we are on the sphere. There is no particular ordering here of the positions on the sphere. So they commute. This implies that the OPE itself is commutative and associative. Okay, so last assumption, which is maybe less fundamental, it's a bit more technically a technical point, is that there exists an identity field I of z, such that, well, I of z times any other field v of z prime does absolutely nothing. I of z, v of z prime is v of z prime. And so let me derive some simple properties of this I of z by computing T of y I of z. Well, that's just T of y, right? Or I can rewrite it as T of z plus something of order y minus z. And now the idea is to compare this operator product expansion with the general formula here. And what you deduce from that is that all the ln acting on I of z are 0 if n is -1 or larger. So in particular, L0i is 0 and L-1i is also 0. From which you deduce that I is a degenerate primary field so this V11 primary field which has a vanishing null vector at level 1. So the identity field must be proportional to that by definition. And you also deduce in addition that from this, comparing this OP with the general formula here, you deduce that L minus 2I of Z is just T of Z. So the energy momentum tensor is a descendant of the identity field. And that explains why 5 minutes ago the conversation drifted. I mean, originally the question was whether the T belongs to the spectrum, but it also became whether the vacuum belongs to the space of states. But that's more or less the same question, because I of Z, which corresponds to the vacuum state, well, is the primary state associated to T, this energy momentum tensor.
I'm sorry, so how am I supposed to think of this in relation with, say, time like Liouville theory or like Liouville theory for C less than 1, where the identity field is believed to be a nonlinear and does this fit to?
No, right. So it's a question of terminology. By definition, my identity field is degenerate. Otherwise, it wouldn't be an identity field. I mean, this I of Z, since it does nothing, it must be in particular constant. D by dz I of Z is 0. And this means that L minus 1, I is 0, so it has a vanishing null vector. What happens in the Liouville theory with C less than 1 is that you have a field of dimension 0, but it's not the identity. And that's the distinction I made between a non-degenerate primary and a primary. Right? So this field of dimension 0, it has a null vector, but the null vector doesn't vanish.
This field has non-trivial correlation function.
Sorry, this field
has non-trivial correlation function.
Yeah, right. In general, if you have a field of dimension 0, its correlation functions can be non-trivial. You can look at the generic 3-point function, which we'll write in the next course, and you put one dimension to 0, it doesn't make the whole thing trivial. It becomes trivial if you insist that your field also obeys this null vector equation.
So generic is really non-unitary.
Yeah, C less than 1 Liouville is non-unitary, right?
Just to be sure again, so do you assume that there is an identity?
Well, it's a bit like T. I mean, it exists in the sense that it's consistent to add it in any correlation function, but I could define my theory consistently without it, in the sense that it will not necessarily appear in the field. Okay, and to finish this course, well, we'll have to do really one of the most technical calculations ever. Well, I mean, of this whole series of lectures. And that's because, I mean, we have introduced basically the basic axioms and the formalisms, but now it's time to really derive some results, right? We haven't so far derived many results. Well, maybe some results about representation theory, but now we want results about field theory. And the first result we need is what is the OP coefficient? And the claim is that conformal symmetry will determine basically how this depends on Z1 and Z2. And it will also determine, it will also say that if you know the OP coefficients for some primary field here, you can deduce all the OP coefficients for its descendant fields. And that's a very strong statement, which is why in two-dimensional CFT, well, you can hope to have exact results. So to derive this, to compute this OP coefficient, well, the basic ingredients are to use, well, conformal symmetry, and to do that we use the energy momentum tensor. And the other ingredient is to use the associativity of the OPE here. So the calculation starts with introducing the integral of t of y next to an OPE of two primary fields. So here I'm taking primary fields just for technical simplicity. I could do it with other fields, but it's simpler that way. So and then I'm taking a situation where the integration contour is around the positions of both fields. So let me write it like that, and then the usual factor 1 over 2 pi I. So I want to compute that. So basically, there are two ways to compute that. Either I first do the OPE of these two fields, or I do the OPEs of t with each field first. And then I forgot an important ingredient. I mean, I want to compute that, but I want to generalize it a bit. So I want here to add a factor y minus z to the y minus z2 to the n plus 1 for any n. So let me write it more cleanly, maybe. So here I'm putting a factor y minus z2 n plus 1. Okay, so let's say the first way to compute is to first do the OPE here. So I don't know much what is going in this OPE, but what I'm assuming is that this OPE, v delta 1 v1 v delta 2 v2, contains a primary field here, some v delta at v2, plus its descendant. So L minus 1 with some coefficient times L minus 1 v delta of v2, etc. So, well, this one also has a coefficient, of course. So, in fact, I'm considering only the terms of the type sum for L, the creation operator of T delta 1, delta 2, delta L of v1, v2, L v delta of v2. Right? I mean, all these fields, well, they are supposed to be linearly independent, so I'm allowed to focus on one primary field and forget all the others, and just look what is its contribution to the OPE. So now, if I apply this integral of t of y to this OPE here, well, here I only have fields at the position z2, and I have chosen here a combination of t, which is supposed to give me, in fact, that this combination, the action of ln over on this field. So I just get the sum, this sum, t delta L, delta 1, delta 2, z1, z2, ln acting on L v delta of z2. Right, that's the first way to do the OPE. No, the other way is to look at this product of two fields. And I can take this contour around the both fields and decompose it into a sum of two contours around each field. With the contour around Z2, again, since I chose this function as y minus z2n plus 1, it will just give me ln acting at z2, on the field at z2. I have to add what happens to the field at z1. So I have to compute something like integral y minus z2 to the n plus 1 t of y v delta of z1. But then I can use the operator product expansion of t of y with this v delta of z1 this is a primary field, so it's given by here. So this is just delta 1 over y minus z1 squared plus d by dz1 over y minus z1 acting on v delta 1. And then I have just these two integrals to compute, two integrals over y. So there's a dy here. And if I do that, I end up with z12 to the n plus 1 dz1 plus n plus 1 z12 to the n delta 1 still acting on my operator product v delta 1 of z1, v delta 2 of z2. So I'm sorry the board is slightly disorganized, but the outcome for the moment of the calculation is that this expression is the same as this one here. There are both of them two ways of computing this original expression using OP associativity.
For the second one, it's a sum over all primary.
Before, in which expression here?
Yeah, there's a sum over all.
No, I'm just taking one primary and its descendants. I am forgetting the rest. I'm computing only part of the OP. The part which is about this.
Would be that.
Yeah, but okay, let's lighten a bit the notation. Unless you find it just not easy enough.
Okay. Sorry, where is v delta 2 z2 in the integral?
In which integral?
The third one, the lowest one.
This one?
Yeah, you should have also.
No, here I'm indicating the part of the calculation which is non-trivial when I compute the integral around z1. Okay, there is a v delta 2 z2, but no, it's a spectator basically.
Okay.
What I have done is to do the p of t of y with v delta 1 z1, and that gives me these things. Well, it also gives regular terms which don't have any singularity, but since everything is holomorphic, these terms don't give any contribution.
Just v of z1, v of z2, they can have a cut. I mean, this coefficient c, they are not necessarily. They can have.
Okay, so yeah, but here, what matters is that everything is holomorphic in y. The only variable I'm really integrating is y. So indeed, the fields themselves, the dependence on z1 and z2, I mean, it could be at this stage complicated, but it doesn't. It's not relevant here. Okay, so we have this this equality, but let's spell it out more precisely in the case n equals -1. So in the case n equals -1, my left-hand side is what? So ln acting on z2 means d by dz2 over dz2 plus here I just get dz1. And this term, well, it vanishes if n equals -1. So dz2 plus dz1 v delta 1 v delta 2 equals, well, equals this one with n with n equals -1. So that's the sum of the coefficient c, l, cl, d by dz2 now, dz2, because this ln acts on a field at z2, v delta of z2. So we get this identity. But now let's use the OP again of these two fields. So that's just sum L of CL. Sorry, there is a L V delta here. L V delta. And then we want to take the derivatives. So the derivatives, they can either hit the structure constant C, which depends on Z1 and Z2, or they can hit the fields themselves. Well, dz1 does not act on this field. So we get something like, well, dz1 plus dz2 CL of z1, z2 sum. So that's L v delta of z2 plus sum. Now the term where dz2 hits the field, so that's CL dz2 L v delta of z2 equals the right hand side here, well, it is exactly the same thing. So the outcome is that this thing must be 0. And since all these fields are linearly independent, it just says dz1 plus dz2 CL of z1, z2, 0. And that's just translation invariance. Now, okay, I've introduced maybe a lot of formalism just to show this trivial result. You may complain I'm not going for the simplest derivations, in fact, but the point is that I have done a general calculation for any n, and I will get a less trivial result for other values of this integer n. So, but we are in a good direction because now C, the structure constant, depends only on one variable, z1 minus z2. And the next case will allow us to determine this dependence. The next case is n equals 0. So for n equals 0, this combination becomes z12 z1 plus z1, well, there is nothing here, plus delta 1 plus delta 2, v delta 1 v delta 2 equals the right hand side which was over there with an L0. So sum L, sum CL, and then L0 acting on L v delta, so that's just delta plus L, so the level, in fact, of this descendant, L v delta of v2. Right? So now we insert again the OPE here, but the nice thing is that we know something about, well, our structure constant CL already. We know it's a translation invariant. So let's see what we get. So dz1 can hit only the structure constant because in this OPE we expand over fields which are all at z2. So we just get a sum of v12 dz1 plus delta 1 plus delta 2 acting on CL, right? And then L v delta of z2 has to be equal to this thing. And again, all our fields are linearly independent, so eventually we end up with this equation plus delta 1 delta 2 minus delta minus L acting on CL is 0. And this determines that CL depends on Z in the following way. So CL Z1, well, let me write it elsewhere. So CL Z1 Z2 is Z12 to the delta plus L minus delta 1 minus delta 2 times some constant now, which is CL, which still depends on the dimensions, but which no longer depends on Z, because the Z dependence is fixed. So we have reached the first goal, which is to determine for OP coefficients here depend on the positions. And we are left with unknowns, which are no longer functions, but which are just, if you want, OP structure constants.
It should follow from this Polyakov formula for 3-point function.
Yeah, you can get pretty much equivalent statements by studying 3-point functions. I'm not sure if it's Polyakov, but maybe. This is technically equivalent, except that when here in OPs you have dependence only on 2 variables. In a 3-point function it's 3, but okay, it doesn't make a fundamental difference. Okay, so I fear that we're running out of time. I'm not sure if I should derive the next big result, which is that if you know the structure constant for the primary, you can deduce the structure constants for the descendants. Maybe we can save that for next time. And stop here for
maybe there are questions.
Yeah, so this identity field, I was slightly, so it's the one where you quotient it out, right? That's how you can get L minus 1 on. It's not the full module, it's the quotiented one that.
Yeah, right. So the identity field is the primary field of a representation, which is indeed a quotient. So this field belongs to the representation Verma module with dimension 0, quotiented by the Verma module with dimension 1.
Also online, if you have questions, you may switch on the mic and talk. No signs of activity.
Okay, so well, you can also have questions over lunch if you want. So.
Okay, so we will meet at 12:30. It's okay.
12, okay.
And if I reminded the last, if you need the certificate, please sign this. Okay. Okay. So see you next time.